So before you guys all came in, I hope that you all got like a yellow USB stick. So it has everything from the dependencies that are necessary to run H2O to basically the H2O installation itself and the presentation and scripts that you might need to run along with it. If you're adventurous, you can try to code everything yourself, but there scripts are there basically as an answer key or just for you to follow along. So like Vinod said, I'm a sales engineer here at H2O. Today's going to be really a hands-on part. So as much as possible, try to install, even if it's difficult. There are people around the room that's going to help out in case you have any issues. I understand if you have Windows from big corporations, you might not be allowed to download certain things or load certain things from USBs. Just wave us down and we'll figure it out. So the only prerequisite for running H2O, and this is available in the flash drive if you don't already have it, is a 64-bit version of Java, 6 or newer. H2O itself is just a jar file, so the entire software is self-contained to launch as a Java virtual machine. So the only prerequisite, if you're not going to use it with R, if you're not going to use it with Python, the core computation engine itself is just a JVM. And so you only need Java to launch it. So there is a 64-bit version in the USB drives that you should probably install if you don't have one. The consequence of not having the 64-bit version is that you will not be able to launch an H2O cluster larger than 1 GB, and which could be fine because the data set itself is about half a gigabyte. So you'll be able to read it into memory, and you'll be able to do some modeling, and it'll fit in memory. The issue is you might want more memory to do multiple models, to do cross validations. So things like that, I would recommend launching larger than 1 GB at least. So for this hands-on session, I would recommend that you follow through one client interface. The way that H2O works is that all the client interfaces flow. Our Python goes through a REST API. So everything hits the same REST endpoint in order to execute or tell H2O to execute a command and a task. So there's no point in trying to execute it from Flow and R and Python. So I would recommend as much as possible to just pick a language and stick with it for the rest of the talk. For people who are not R or Python users or do not want to install H2O today, an easy cop-out, I guess, is to just use Flow. So Flow is our web-based UI that comes prepackaged with H2O. So it can do some of the basic REST commands that you're allowed to do in R and Python. It might not be able to do as much of the munging steps or do things like imputation or feature engineering, but for the most part, it can import a data set and it can allow you to inspect the data and then build a model. So for people who are mainly interested in H2O's library of algorithms, that might be a good place to start. So I'm going to pause between slides so that everyone can try to run this. But basically, the H2O zip drive is our installation. So H2O 3.8.3 is the installation that we'll be working with, and it should be in your either Windows or Mac OS directory. It's a zip file. All you have to do is unzip it, and either from the command line run java-jar h2o.jar, which will launch the JVM. You can even specify how much memory you want in the JVM using -xmx 4 gig. That will launch a 4 GB H2O instance. And the moment you do this, you should be able to access Flow through a web browser at localhost 54321. Another way to do this is if you're a Mac or Windows user, you should be able to just double-click the jar file, and it should just run this command automatically and launch with 1/4 of the amount of memory that's allowed on your machine. And so this is what Flow looks like. I'm going to go over a quick demo of it before we go through the walkthrough. But it's sort of a notebook-based UI, and you're allowed to sort of point and click through the entire interface. But what's generated is essentially CoffeeScript code that you can rerun programmatically after you built your first flow. There's a few guidelines. There's some quick start videos. So for people who don't really know much about H2O, this is sort of a good place to get started. So for our users, unless there's any questions about launching, how many of you can launch the, OK, a few, less than I want. So for the R and Python users, there are the R packages in Windows or Mac folder. Under R packages, there's a few dependency packages that you might want to install: statmod, rcurl, JSONLite. All you have to do is do an rcmd install of the packages. And then install the H2O package that's in the H2O directory underneath the R subdirectory. The other way to do this is, if you have internet access, and the internet is actually fairly good here, is install it straight from CRAN. And so all you need is install that package as statmod, rcurl, JSONLite, and then you install H2O. And the way to check to make sure you actually installed all of it properly is just to launch the H2O library and then do initialization of an H2O cluster. So I'm just going to pause here for a second so people can maybe run through these commands if you haven't already installed the H2O R package. There. So I'm just going to look at the clock, and I'm going to give it about a minute or two, just in case you need to download the package. The internet should, oh, you don't have internet? Let's see. So the internet should just be H2O open. And the password should be GO H2O Tor, or what was the password?
Go H2O NYC, but I think it's better to use the zip drive because it's 120 megs.
Yeah. Oh, OK. Yeah. So again, I'm going to show, while people are trying to run this, I'm going to show in a terminal what you should essentially see from the zip drive. So you essentially have a zip drive called H2O Tor. And then if you're a Windows user, cd into Windows. I'm going to make this bigger so it's easier to see. PWD here. OK. So there's installation for, oh, sorry, here we go. There's an installation for RStudio. There's an installation for R packages. And then there's a R installation inside the H2O-3 directory. So what you essentially want to do is go into R packages and do a rcmd install of, let's say, rcurl. And then subsequently for all the packages you need. So statmod, rcurl, JSONLite is essentially what you need. There's just 3 here. And the same goes in the Mac directory as well. So I just OSX, R package, Mavericks, or Snow Leopard, and then just, again, rcmd install. And if you have issues trying to add R to your path, what you can also do is, here we go, just go through RStudio or R console and just do install from local, and then basically, install from local, and browse through your local file system and choose the files necessary. And so it's already on the zip drive, so you don't have to access the internet in order to install it. And everyone tries to install H2O all at the same time from S3. It might be an overload. So as much as possible, try to install from the zip drive. OK. And very similarly, for Python users, again, we have some certain dependencies. You need either Python 2.7 or 3.3, and you need a few dependency modules. This includes requests, tabulate, and futures. So again, the Python module itself is available in Windows Python modules or OXX Python modules, and the targz or wheel files are available in the directory. And all you have to do is a pip install or a sudo pip install, and you should be able to install all the dependency packages. And after you have the dependency packages, do a pip install of the H2O wheel, which should be in the H2O installation directory under Python. Again, I'm going to give you guys like a minute or two in case you're a Python user trying to install this. Again, you can also go through the internet and try to do a pip install request, tabulate future 6 from the internet instead of from the zip drive itself. Again, if you have internet, this is all a lot faster and speedier. So if you have any problems installing H2O on Python or R, one quick way to sort of debug this installation issue is to make sure you have all the dependency packages. There's usually just a few, few issues requests installing maybe dependency packages, which results in not being able to install H2O. So either in R or in Python, try to import or to load the libraries in each platform. And then try to do import H2O, and then again an H2O.init, which will start up an H2O instance. And if you can start up an H2O instance from R Python, your job is done. So let me see if I can go. So another minute, and we'll go on from there. And again, if you have any questions at all, when we get into more architectural stuff, please stop me. We have microphones that we can pass out, so I can hear you. OK. Another few seconds. A quick heads up, though. If anyone is using the package rcurl or JSONLite before, they would know that you would need curl config. This is usually an issue if you use Ubuntu. It's not automatically installed. So easy solution is to do a sudo apt-get install of a libdev version of our curl config. So if you can't install rcurl, you know why. So the objective today is just to run through one of these demos. If you can run through it, then you can kind of see how the data moves between H2O and one of these client interfaces, what kind of commands are possible, what you might have to relegate down to base R or base Python, or use in conjunction with something like Spark to do some of the munging steps. I want to go over a very high-level overview of how exactly commands are being sent from R, Flow, and Python over into the H2O executable engine, and then some frequently asked questions about how to write our Python expressions that execute H2O tasks rather than tasks in R or Python. And then there will be a hands-on session that use a publicly available airlines data set filtered down to flights going to Chicago. And we're going to try to predict delays, but not just weather delays. And we're going to try to lump on top of that weather data that we actually collected from Chicago and see if we can improve the ML models any more than the base information that we have from the FAA. And then we'll look over some of the limitations of the models, what we can do further to improve the workflow or the models itself in the end. So I mentioned earlier that H2O, all the client interfaces that talks to H2O talks through a REST API. So when you call a R or Python function call, what you do is essentially the function call itself is a function to do a JSON post to H2O and ask it to execute a command. And on a single node is fairly straightforward. You give it to H2O and H2O executes it. On a multi-node example, for example here, let's say you have a local R session and you have H2O distributed on EC2 instances on the cloud, or if you have H2O distributed on your Hadoop cluster and you want to access data from HDFS and S3, you call a function call locally, and it gets brought over through the HTTP REST API with the arguments to import and the arguments of where the path actually is. It hits the H2O instance that you're connected to, and so subsequently it distributes out to the rest of the peer nodes. All of H2O nodes are peer nodes. It doesn't matter which H2O instance you connect to. It will know to basically distribute the tasks amongst the other peer nodes. And then they'll all go in to HDFS or to S3 and grab at the data. So the data is then read into H2O, and the way it's read in is read in as chunks of data. So bits and parts files are read into H2O until there are no more bits to read, essentially. And what you have here is a distributed key value store. And the frame itself is sitting distributed on that key value store. So the way that we want the front-end user to look at it, though, is just a regular data frame. We don't want you to have to look at the back end and say, well, this is where the chunks are and threads are. So what we return on the front end to the H2O data science user or the software developer is an object that points to that distributed frame. So the object returned in our, let's call it H2O_df, has basic information about where the cluster is, IP import, and a pointer to the data set. So all it needs is the key to which the data is referenced in the key value store. And that is really cheaply created in R. And that, it will contain some basic information about the headers, and you can look at it almost like a data frame. But the full-scale data set, let's say you have a billion-row data set, will never get imported into your local R session. It will be sitting remote on an H2O cluster, whereby there all the computation will be taken care of. So is there any questions about how H2O works with R and Python? And this, this model goes to any client front end that essentially can write and read JSON responses. So as long as you can post the requests and get back, parse through JSON requests, you can integrate H2O into something like Mathematica, MATLAB, Excel. You might have to do XML responses. But Tableau has a connector into R that allows you to basically do simple aggregates that you can express on those client front ends. So for the programmatic user, R and Python primarily, and Scala users as well, we have certain things that you might be familiar with in the base language, that you have a parity function that you would use for H2O frames and with an H2O cluster. And so things like read.csv, read.table, or fread in data.table is relegated to H2O.import file. And instead of reading it into R using read.csv or pandas read table, you call the H2O.import file to import it elsewhere, representing it in R and Python. And then we overwritten some of the methods, like summary. It will be able to detect whether or not you passed it an R data frame or an H2O frame, and then execute the right method. rbind, cbind are prepended with an H2O prefix. Unary and binary operations are as they always are. So I'll show you in a little bit. But if you want to do a columnar transformation, log transform of a column, things like that, we support it on the H2O frame. So you can actually use very similar, or not the same, exact line of code that you would use on a regular R data frame. So all of H2O's algorithm, here I have an example, is GLM. A straightforward example. We've implemented it very similarly with all the parameters that you would normally get in something like Glimnet. So it standardized the data if you wanted to. It has ability to run with regularization. You can specify the regularization strengths. It can run through a lambda search. And so it's not scaling up something like Glimnet. It's our own implementation that allows you to run a logistic regression model in parallel across huge scale data. And this has to be done across all the algorithms that you want to implement in H2O. It's not simply grab a R package and then run it with H2O. So these models, GLM, random forest, GBM, deep learning, they're all implemented in H2O on the H2O's in-memory MapReduce framework. And this means that it's some of the arguments might be different, some of the implementations and parameters might be different, but to call the model build is essentially still the same. You do a glimnet of the frame. You can do an H2O.glm of the frame and parameters. So I mentioned before that this is kind of important, the unsupported functions in H2O. So if you want to use something like a caret package or a smooth function, that is something that is not written into H2O, so we don't support it. One way to get around something like this is to use R or Python as a complement language rather than using H2O to substitute the language. So what you can do is, instead of throwing away all the R packages that you used to use, is be smart with H2O. Read in the entire frame into H2O, splice it, subset it, sample it, and then you're able to take the subsetted data set back into R. There's a function in H2O called as.dataframe, which is also a new function, a new method that specifically works for H2O frames that will bring your distributed frame back into R. So if you just want to edit, let's say, one column, let's say you want to do an imputation that is very specific to R, you want to use the mice package, you can bring that column back into R, run that specific algorithm, and then re-import it into H2O and C-bind it back or append it back to the original frame. So the scripts that I have runs through a small, relatively small airlines data set because I filtered it all down to flights going specifically to Chicago because I have Chicago weather data. You can obviously, when you're at home or if you're interested to do this, there was actually a contest, a data science contest to try to predict things like weather delays and delays for airlines. The entire data set is available online. It's hosted on S3. You can grab at it and try it yourself on the larger data set. We're going to run through a simple logistic regression model. We're going to run through a GBM gradient boosting machine model. We're going to review some of the model outputs in R, as well as how it's represented in Flow. So in H2O, you get the best of both worlds because everything is through the same DKV. You can manipulate and run things in R and Python, but then view those models or things that you've done differently through Flow, which is a more graphical interface. So instead of just getting, this is my AUC, you get an ROC curve. You can look at the different thresholds. You can point and click and sort of look at your true positive and false positive rates and pick the best threshold, which is not really interactive graphical capability that's available in R at the moment. We're going to also look at joining the flight data with weather data and then rebuilding the logistic regression model and the GBM model, and then, again, reviewing the new model outputs. So let's see here. See how many of you have actually successfully installed. Sorry, give me 1 second. I'm going to run through the demo once in Flow, and then we can go through it together. So if you're a Flow user and you already have it up, maybe you can run through this with me as I go along as well. So the way that Flow works is that it's supposed to allow you to point and click through the entire interface without you having to write code. So you can go to the localhost 54321. You can click on Import Files. And what will happen is we'll have, sorry, give me one. I have to start up an H2O instance. Here we go. I'm starting up an H2O instance. OK, here we go. 4 GB. So in Flow itself, when you click on Import Files, it should automatically detect your file system. Right now, this is just a local file system, so it's fairly straightforward. User, Amy, desktop. I have my data in H2O Tour, in Intro to R Python Flow data. And I have a specific data set that's for Flow, where I've joined the data, and it's weather with flight data. And I can just click Import. This works for your local file system. This also works on HDFS. If you type in HDFS:// on a Hadoop H2O cluster, it will automatically detect the name node and detect the file system, the distributed file system, and auto-complete your path in HDFS as well. Same with S3 buckets. We've also recently rewritten our S3 parser, so we use S3 libraries directly, and you should be able to more easily now get an auto-completion for your S3 buckets and directories. So I'm just going to hit parse these files. Notice I'm not writing a single line of code. All of this is pointing and clicking. But what is automatically generated as I point and click through this entire interface is a CoffeeScript. So when I ask it to import code, what's going to save when I finish with this flow is import files argument. And this is exactly the same thing with R and Python. There's a function call. There's an argument for the function call. And this is generated so that you can save it and reload a flow. So someone who's not a Python or R user can still write repeatable scripts that and build models, essentially. So what you'll see here is H2O has two-step process for importing and parsing the data, which is import and parse. So you imported the data, and now you want to parse it. And the parse step is really about specifying the schema. The schema is automatically detected for you by our parse guesser. But if for any reason we didn't do a good job and we got some of the column types wrong, you can always specify ahead of time to change these column types. And you can do this again through R and Python. So we're just going to import this flight data really quickly. So it took about 4.6 seconds to import this data set, which has 1.7 million rows, 57 columns. So it's relatively small, but big for the cluster that I have running. You can see that you can grab the first 100 rows for the data set through Flow. So you can inspect it through cells. And I can do things like DD, which will delete a cell. And here, let's say I want to split this into a test train split. Create. And then we're going to pick the 75%. We split into 75, 25%. So the 75% of it, obviously, we'll use for training set, and 25% for validation set. Again, you can look at your frame that is created after you did a test train split. One thing to maybe do is when you create these, when you subset your frames, it's maybe good to look at the distribution of the columns, particular columns and response columns that you're going to use in the model build. For something like I want to predict departure delay or arrival delay, I might look at a specific column. And if you point and click through the different column names in Flow, you'll get either a distribution or a frequency count for all the levels in a categorical column, depending whether or not you have a numeric or categorical column. And you'll see that there are abilities to impute missing values. So this is particularly important for GLM models. And by default, that might throw away missing value or entries with missing values. Our GLM in particular does, by default, mean imputation, which you might not necessarily want either. So you might want to do the imputation by hand yourself and then run the GLM model rather than have GLM just do mean imputation for all the missing values in your data set. So we're going to just build the model real quick here. We're going to pick a generalized linear model. We're going to have the 75% for the training set, 25% for the validation set. The response column is to predict whether or not you arrive late, which I always thought was more important than if you were delayed. So the flow interface is a little different in that I'm going to ignore the columns I select are ignored. And then I can go in and deselect all the ones that are I want. So things like the time of the year you want it, where it's flying to, which is only Chicago, so it doesn't matter. But where it's flying from, for example, would matter. Which flight, which carrier you use will matter. Origin, here's origin, day of the week, the distance that you have to travel. Are you more likely to be delayed if you have a long-haul flight versus a shorter, SFO to Seattle flight? You want to make sure you unclick is arrival delay. So response column is part of the model as well, and you want to make sure you uncheck that to be part of the model. Going down, travel time, the temperature, humidity, all this stuff we want in the model, so I'm just unclicking it here. And if it has something like enum level 1, it will automatically be thrown out. And even in this section, you'll see that there are small summaries about the frame. So something like events, for example, is 71% NA. So if there's no events, then there's nothing recorded down. And those columns are going to be NAs. For enums, it's not going to matter as much because it gets automatically expanded out. But for numeric columns, that might be a problem. So you can select the distribution you want to build on. So we're going to pick binomial for a binary classification problem. You can muck around with things like regularization strength and running lambda search. You can automatically standardize the frame before you run the model build. So a lot of things is happening on the back end before it even starts building the model. You're given a frame that has a categorical column with many different levels. H2O automatically does basically one hot encoding to expand those categorical levels out to the model matrix that you would normally use in GlimNet. So you can pass it the model matrix, or you can just pass it a standard frame that you have sitting around instead of having to go through that extra step. It'll standardize the numeric columns, and the categoricals are just expanded out to 0 and 1s. So we're just going to go down here and just click Build Model. There's a bunch of parameters there that I probably did not go through, but we're going to just build the model really quickly so that we can go through the R and Python scripts as well. And voila, you have a model output in Flow. And you have the AUC value, the ROC curve for the training and validation set. You can, as I mentioned before, you can point and click through this curve. So you see the false positive rate and true positive rates that for each given threshold. You can see the thresholds are calculated here, almost per 0.001 change. The confusion matrix for each threshold, and then the standardized coefficient magnitude. This can sometimes be used to do feature selection or just to see how your regularization strength, which features got dropped out, or which features got shrinked, or which one are still important in the model despite all the regularization. And then at the very end here, for the software developers in the room who care, this is the plain old Java object, which is exportable outside of H2O. So the model that I just built, this could be built by a data analyst, not necessarily a data scientist, is pointing and clicking through the entire interface. But what's really being built on the back end is a Java model. So you can export this out essentially as Java code. You'll see the 5-line of code here. Where you curl the H2O gem model jar file, and you curl the H2O GLM code, it's Java code, and then you can compile it completely outside of H2O. And this is great for people who want to use the model in whatever scoring server they have or production environment that they have. So we have people basically pulling this from H2O and plugging it into something like a Hive user-defined function to score and batch across data that's already sitting as Hive tables. You can plug this into a web application, and there's going to be a talk about productionalizing models right after this, so it'll go a little into the different ways you can use the plain old Java object. So what I just did, I want you to replicate. So as much as possible, try to get the data paths to get to the right location and try to run the flow or try to run the R and Python script. One way you can do this automatically is in the directory. Here, let me show this really quickly. Assuming this is your USB drive, in intro to R, Python, and Flow, there should be a Flow directory, a Python directory, and an R directory. Right here. If you're an R user, in the R directory, all there is an R script. And you need the R script and the data that's in the data directory, just flights and weather. If you're a Python user, there is a Python script or an IPython notebook that you can open with Jupyter. And again, the data is still in data, and then you need the flights data and the weather data. If you're a Flow user, there's limitations to things like how you can do joins, you can splice your data, merges. So what I did is there's a flow that you can upload into your flow that you've just loaded. But the data that you would use is it's separated out as for Flow, specifically for Flow users. So it's data that I've filtered specifically so that it only has data going to Chicago from 2003 to current day. And the for Flow merge data in particular has merged it with weather data set. For R and Python users, we're going to do this by hand. We're going to show you how you are going to merge flights and weather data, the function call, and the syntax for something like that. So again, through the Flow UI, if you're loading the flow from disk, there's on the very top, there's flow, cell, data. So underneath flow, you can open up a local flow. Pick the flow from your USB drive or from your desktop if you moved it onto your desktop, and just open it. And so what should be automatically generated is the import files, cells, parse files are the first things that you'll see. And then right over where I have the little yellow button there, that's how you run the entire flow. So if you don't want to run it by hand, if you don't want to do Control-Enter and run it cell by cell and see what happened, if you just want to run it all and just see the graphical outputs, you can click on the Run All button and basically ignore when I run through it cell by cell. So we went over this already, how to start up a H2O and load a preloaded notebook. For Flow, it's a java-jar command or a double-click on the H2O jar file. For our users, is library H2O. You start up with n threads equals to -1. This in particular is because you want it to use all the available cores on your machine. If you leave it by default, it will only use 2 cores of your machine. And the same with Python. You want to import H2O, and then you want to do an H2O.init n threads equals to -1. And I just want to show you really quickly the different, how the same command is expressed differently in Flow, R, and Python. So in Flow, you've seen earlier, it's just import files as coffee script. You set up the parse path, set up the parse. In R, it's just an H2O.import command. You can split it up into import and parse separately, but by default, we'll do the guest parser. And if you don't tell us we're wrong, we'll go ahead and parse it in one function call. So what you want to do is import the flights and the weather data set, just doing an H2O.import file call. And for Python users, it's basically the same syntax, the same function call. We just name it differently because R and Python has different sort of naming conventions. Things are camel case versus underscored. So there's slight differences there. But you can see immediately that it translates over really easily because it goes through the same REST API. What this means is scripts that you write in R, you can translate to Python. So people who have teams with heterogeneous skill sets means one person can use our code, build a model that translates over to Python code. And this allows for a little, some level of collaboration as well. And things get a little stickier when you have to use packages specifically for R Python. But if it's just H2O, it's really easy to translate. So the data set we went over earlier, we want to use it to predict arrival delays, sorry, not departure delays, using the historical airlines data set with destination going to Chicago O'Hare, because it's the most frequently reported flight in the data set, so I picked it. There are a few enumerator columns. Origin, unique carrier, have a cardinality of 132 for origin points and 10 different levels for unique carriers. Numeric columns include day of month, year, day of week, month, and distance. So not very many features to predict arrival delay. So I'm just going to go through this in R and Python to show you. First in R. So in R, I'm going to run this, and I run it along with me. But you load up the library. You do an H2O.init. This is where you might have to change it a little bit. I have the base path set to my desktop where my data is sitting. So please change the path to wherever you have loaded the H2O data. And then we execute the H2O.import files that I mentioned earlier. And so little arguments here, you can specify the destination frame so that it's easier to look up later. If not, we automatically give it some sort of frame name that you might forget. So for both data, and we can do a dim of the frame. So dim flights.hex, which is what you can do on our data frame as well. You can see this flight data set, unlike the one I showed you earlier, is, I think, 4.7 million rows, 4.7 million rows by 31 columns, and imported in less than 30 seconds, 15 seconds. And while it imported, it also calculated the base statistics that you saw earlier. So everything from the min, max, mean for numeric columns and the frequency counts for categorical column is already calculated. And what you can do is just call an H2O.describe, which will, sorry, there's a typo. It should be flights_hex instead of flight hex if you hit across that problem. H2O.describe, which will return a table that is pretty much identical to the one that you saw earlier in Flow. So you see this is sort of the columns, the type of the column, the min, max, mean, the cardinality, the standard deviation for a numeric column. I just want to pull back to Flow so that you see, get frames. You see that exact same data set I imported using R code is available in Flow underneath flights.hex. So you can see it's 4.7 million rows, 31 columns, just like it said in R, and the exact same summary that you get returned in R. There's certain functionalities, things like his, for example, histograms in R. You just prepend H2O.his, which will basically calculate the bins and bin the different entry points for you, and then return a plot of the summary in R using just the base R's his function. So here, I just did a histogram of all the flights per year. So you can kind of really clearly see how many flights per year going to Chicago. In particular, the last year seems to have spiked a lot. What else you can do is do something a little more generic. So a data scientist might want to build a predictive model or even just explore the data a little bit. So if you're a data analyst, for example, and you want to see basic information that you might see in Tableau, if you drag and drop a few points to see things like how many flights per year, how many of them were delayed, and how many of them were weather delayed. You can write a simple few if-else function to calculate numerically if your arrival delayed or if your weather delayed. And then you can do a simple group by function similar to what you might do in ddplyr, or dplyr, is you can group by certain columns and ask it to execute some primitive R functions. So here I'm saying the dataset flights underscore hex is the data I want to subset. I want to subset by the year column. I want basically the number of flights per year, the sum of all the arrival delays, and the sum of all the weather delays. And what gets returned here is a H2O frame. So you can see that the H2O frame itself is only six rows long. But the frame, the actual frame sitting in the DKV is 27 rows long. So you can see even for a smaller frame, it's truncated. But what you can do at this point is, because we tell you how big that resulting frame is, you can bring it back into R, which is what I mentioned before. You can do an ASOT data frame of this R H2O object and bring it back as a regular data frame. So we're just going to call it flights count df and do an ASOT data frame. So now what gets returned is all 27 rows worth of data. And I'm just going to plot this really quickly as a bar plot. So instead of this histogram, what you get instead is this other nifty bar plot. And you can see something really clearly from the bar plot is I originally want to predict weather delays. You want to look over the data set, and what you notice is for every flight before 2003, there are no values for weather delays. They weren't calculating why the flight was delayed. So it doesn't make sense to use the rest of the data if it's not even basically labeled correctly. So what you want to do is filter out all the flights before 2003. And this is a quick way to examine your data, maybe subset it to a problem set that you actually want to solve. And the line to basically filter by year is very similar to what you would do in R. So you have the frame, you have the column name, and then you just specify the condition by which you want to subset it, and you rename it back to flights.hex. So now instead of 4.7 million rows, we can do a dim on the same flights.hex frame, and now it's 2.2 million rows. And then I'm just going to go into Flow and show you the exact same lines of code that you would have done to do it the exact same thing in Python, in an IPython notebook. You simply import the H2O module. You'll see that I've imported specifically H2O estimator, GLM, and GBM from the package as well. This is sort of to mimic the scikit-learn syntax, where you load an estimator and then you fit it to a frame that you have. I can do a H2O.init. It automatically detects a 20-minute long running H2O instance. So it connected to the same cluster that I started from R, essentially. You can see that I started with 4 gigabytes worth of memory, and this is why if you have only 1 gigabyte H2O instance, I really recommend that you you try to upgrade to a 64-bit version of Java and with a little more memory, because already I've used up about 1.2 gigabytes worth of memory in H2O. And so you can see I have 2.84 gigabytes free. Going down, again, I define the path. It's basically almost line for line the same code. I can import the flights and weather data. And let's see, here we go. You'll see that there's a slight difference in how you show the data set. So if you want the first 6 rows, for example, in Python, you enact a method on the object, on the H2O frame object. And if you do, let's say, flights.hex and tab complete, it will show you all the supported functionality for that H2O frame. So you can do things like, oh, you want to turn it into a numeric column. If you want to take the absolute value of a column, all of that is available for you to sort of peruse if you just do tab complete on an object. So again, it's very similar lines of code. You want to do a group by. You create a grouped object, and then you enact on it counts for the number of flights and the number of arrival delays and weather delays. And then you can turn it again back into a data frame, or in pandas is really a pandas frame. You can also import it back into our Python as a list of lists. So all of that is available to you so that you can toggle between base Python and H2O Python. So the step that you can't really do in Flow, I mean, you can't subset in Flow. You can't do any of this count and group by stuff that you might want to view the data. Another thing is to create parameters, append them back to your original frame. And this line of code right here, the parameter creation here, I took the airline's arrival time, which is given to me in military time. It's given to me as 1351. So it's really 1:51 p.m. So I want to calculate this in terms of the minutes elapsed since midnight instead of this time that I can't really use. So what I do is I do integer division to separate out the number of hours. Then I take the module 100 to separate out the minutes. And then I calculate the arrival time in terms of minutes since midnight. And then I do the same for departure time, estimated departure time. So this is not the actual travel time. This is what it was supposed to be the travel time, what they said that under best circumstances, this is what should happen. So this section of the code is particularly interesting because if you swap out flights hex for a regular R data frame, this line of code, this section of code will still work. So unary and binary functionalities are supported by H2O in that you don't have to care about things like prepending an H2O prefix or wondering if it's supporting it or not. It works fairly intuitively. And then I'm just going to append that travel time, which is the difference of departure time and arrival time, is a total travel time you would take for a flight. And we'll just append it back to original flights.hex frame. So originally, we had maybe 31 columns. I've added about 34 columns. It referenced back to the same data frame. We just basically mutated it to add more columns. So this is sort of the data munging step. And if you guys have any questions, I'll pause right here. If you have any questions about supported functionalities or things you might want to do in R and Python. If not, I'll wait around so people can catch up. So the next step to this is to build the ML models, to build the predictive models to predict whether or not something is going to be arrival delayed based on weather. And first, we're going to do it without weather data and see how it fares, and then append the weather data. So the line of code is fairly simple. And this, because all the H2O algorithms are written with a similar framework in mind to do classifications or regression problems, what you can do is define some basic similar variables. Things like, what's your predictor variable? What's your response variable? My x, my y. Do a test train split. So now you have a test train split that can be used across all the different classification or regression algorithms. And then in here, for GLM, for example, you specify your x, your y, your training frame, your validation frame. And then you change a few parameters that's specific to each algorithm. So in GLM in particular, family is, the distribution is called family rather than distribution. And it's binomial, not Bernoulli. So little differences there. But you can also, alpha value for GLM in particular is different from the other algorithms. So things like that might change. I want to run with lambda search. I'm just going to execute this line of code right here. But those same 4 parameters, my x, my y, train, valid, that could be translated across all the different algorithms fairly easily. So instead of building just the GLM model, you can build many different algorithms, many different models from different algorithms, and see which one works best. And what else you can do is run, because it runs so quickly, you can, instead of doing a test string split, you could run cross-validation instead. It can run many folds and basically build your main model based off the cross-validated results. So it built the GLM model, and then I'm just going to call the GBM model as well. The only thing that changed is distribution is called Bernoulli instead of binomial, and I can specify the number of trees I want to build. And while that's building, I'm going to just toggle back over to flow. And I can call get models, which will give me all the models that's currently being built, including the one that's not finished being built yet. This one's at 62%. I can look at the GBM model as it's being built. You can see the number of trees that it's at. It's only at 3 trees. But you can keep refreshing this as it's being built, and it'll add the scoring history per tree. So now we're up to 35. So this is sort of a nifty tool if, let's say, you're building a model for 2 hours, and you want to inspect the progress of that model as it adds trees or it's running multiple epochs in deep learning, for example. This is a good way to maybe prune your models early if you start to see in the scoring history right here, it's not overfitting yet because you have the orange line, which is your validation set, and the blue line, which is your training set. They're still sort of the log loss of both of those frame over the number of trees is still decreasing. You want to keep building it. But let's say if at any point, if that orange line starts to curve up, if the log loss starts to increase after a certain number of trees, then you sort of know, oh, I'm starting to overfit. We should maybe prune the trees a little early and take the POJO from there. So the model is probably finished building, and I can just hit Control-Enter again, and it will refresh for me the GBM model, which is 50 trees. And you can see that I can probably continue building for more. I don't think it's really gotten to the best model that it possibly can. And you can look at the AUC value as well as the variable importance for GBM. So earlier we looked at GLM, which has the magnitude, standardized magnitude coefficients. Here we have the variable importance for GBM. So this is one way to understand what a not very interpretable model is doing, which variables were important in the model, rather than sort of this is just a prediction, this is the score. And the way that variable importance is calculated, which is not as interpretable as GLM, because GLM will give you a direct coefficient for the relationship between the feature and the response variable. Here you get how often a variable was used to build the model and how significant it was when it's split by that certain feature. So it might have split by unique carrier many times, because there's so many levels, it helps to improve the model. So you can see that unique carrier is sort of really high up on the variable importance list. And this is relative variable importance. So the max is 1 here. And then travel time's all the way at the bottom there. So I'm just going to show you the results from the GLM and the GBM model on the slide here, so we can sort of look at it really quickly. Without the weather data set, you can sort of see that the AUC for the data without weather, it's around 0.72 for a GLM model. You can see that it's mostly split by unique carrier, so which airline you take versus and where you fly from is the most important in this particular case for the GLM model. And the GBM model, you can sort of see the scoring history that we mentioned earlier, and the AUC is 0.80. So it did fare much better than GLM out of the box, even though we ran with lambda search as well. Assumingly, it picked out some nonlinear interactions that GLM did not. So if we join it with Chicago weather data, and we can join it with data that's from, instead of just destination weather data, we can also do arrival. But in this particular time, I don't have that data on hand. You can also easily scrape it from the weather, any weather data set, weather website, and grab the weather for the last 20 years for other airports, origin airports. And the weather data basically has many numeric columns. It has the min-max mean for the temperature, the humidity, the visibility, the wind speed, and the precipitation. So if it's raining, the inches that it has rained. And then it has one categorical column, which is called event, which you guys all saw was 71% NA. And this is usually the presence of fog or snow, thunderstorm, which you would think is particularly important in predicting whether or not a flight will be delayed, more so than something like temperature. If something is cold, it doesn't really matter unless there's snow on the runway. So I'm going to, again, toggle back to our studio here. I'm going to show a quick table of the results from the training set and the validation set without the weather data set. I'm going to join the flight and the weather data set. And so H2O has one of the fastest merge and joins out there. It's fairly easy to use. You specify the 2 frames you want to join by and the columns that you want to join by. And I think Matt Dow, who wrote Redux sort for H2O's group by, has done some benchmarkings where it joins a billion row with another billion row data set in sort of record time, essentially. I don't remember the exact time, but it's on the internet somewhere. So we're going to just do the merge, and we can see here we go. The dimensions of flights hex, the dimensions of weather hex, and then finally the merged data set, which is instead of 34 columns or 27 columns, the resulting frame is 47 columns. And you can see the weather data set is fairly small, but the merged data set essentially retained all the flights available in flights.hex with new features. You do the same thing again. You do a test train split. This time you specify a different set of X variables. You have a lot more features you can run with now, in particular just the weather. And you call another GLM model build, or you call another GBM model build. And you can do this in the loops so that it runs a lot smoother when you change certain things. You can write everything into a function and just change little things in that function and just ask it to run. But we're just going to break it out so we can see it more easily. I'm going to run, again, GLM with lambda search here. It's going to take maybe 30 seconds to a minute. And then we'll run weather delay for GBM. And then we can look at the results in a table in R once it's done. So while it's building, is there any questions about the algorithm or about how any of it works? Nope. Oh, yes?
I have a question about fuzzy merging.
Sorry, what?
Like fuzzy merging.
When we merge? Yes.
Yeah, like 2 text strings that are not nearly identical.
Oh, I see. Yeah, no, at the moment, we don't do much for text. There's actually a relatively small subset of functionalities that we support. Things like doing a substitution, a global substitution, doing stir splits and things like that. But beyond that, we import the data as, if it's a string column, either as an enum or a string. So there's really not much, you can't really do a fuzzy merge, essentially, on text data. Yeah. But you could do that in Spark. And if I had time, I'll show you a sparkling water demo that does involve cleaning out data, text data in Spark, and then subsequently loading the numeric representation of that text data into H2O to build an H2O predictive model. So the GLM model is done building, and I'll just show you via the slides what it looks like. So everyone should get an improvement on their GLM model. So it went up from 0.72 to 0.79. You can see the standardized coefficients. It still hasn't changed too much. The unique carriers that mattered before still matter, with the exception now you have events, fog, rainstorm, snow, thunderstorm in there at the top 20. So obviously, if the weather is dreadful and you have fog, rain, snow, and thunderstorm all at the same time, which is what that level means, you're more positively correlated with being delayed. And again, with GBM, the AUC before, I'll remind you, was 0.8. It's jumped up to 0.57 now. And again, I can actually build with more trees. It doesn't really look like it's actually done building. So there's sort of room for improvement just by increasing the number of trees. And you can see the variable importance that has or hasn't changed, most in particularly origin and unique carrier still on the top. But you can see things like precipitation in GBM model seems to come out on top more prominently than GLM. Or actually in GLM, you can look at the full list, and it'll probably come up as an important variable as well. Events are usually split by quite often as well. So it's usually if it's snowing or if it's raining heavily, and major events that really matters when it comes to predicting delays, weather delays. So we're going to go through an overview of the data right after we finish running it in Python and R. So we've finished building the two models, and I'm just going to create a data frame that expresses the GLM results and the GBM results. And as I said before, the GLM AUC value is 0.8 almost. GBM is 0.5. And you can see the training set and the validation set is fairly similar. You can run this again with info cross-validation rather than doing your own test train split if you want to further verify the results. But it doesn't seem like the model is overfitting, and in particular for GBM, that's particularly important to look out for overfitting. So I'm just going to go over the Python code really quickly as well. I mean, you guys can Control-Enter and execute this in, the entire time I was talking. But I just want to note out little differences in the R and Python code. In particular, parameter creation is fairly similar. The unary and binary, like integer division, has a different operator in Python than it does in R. But little differences like that. If you execute the code, again, you set my x, my y, this time as a list, and then you do a split, which in Python is slightly different. You do a random uniform of a specific column, and then split by a random ratio, so 0.75 was ours. You can see that we imported the GLM, or generalized linear estimator, earlier, so we can define the model that we want to build, which is a GLM model with all these parameters. And then we want to train on that estimator object with the x and y variables that we have and the frames that we have. And the same goes for GBM. Let's see. And again, I'm just going to further go over some of the changes, but things like merge, for example, instead of H2O.merge is a merge operation enacted on a H2O object. So little changes. And you can, again, also print out the results as sort of a table to review as the same as H2O in R. So I'm going to go over a quick overview of what we learned from that small exercise, or at least what we observed from that small exercise. The GBM model, in general, with the same feature set, outperforms the GLM model. One's a linear model, another one is tree splits, so there's more opportunities to learn nonlinear interactions. The GLM models are more interpretable. It has beta values that directly correlate with the response variable, and a value that directly tells you how much probability it contributes to the end score. But what you can do with H2O is combine the two models for a model that has the nonlinear interaction as features in a GLM model. So what you end up with is possibly a more performant GLM model because you use this output from a GBM model, but it's still interpretable for a front-end user. And this is particularly important if you work in an industry like healthcare or in marketing analytics. You want to know exactly what the features mean for your response or your score. But most importantly is usually insurance and healthcare, that really the doctors care or the insurer cares exactly which feature contributed to you being sick or over the top in terms of whether or not you're allowed to have certain insurance policies. So the way that you can improve the GLM model, we haven't really shown it here, is do more feature engineering. You can use things like GBM. You can use things like deep learning, for example, to learn features automatically. You don't have to create the interaction terms yourself. You could. There's an H2O.interaction function that allows you to create pairwise interactions between categorical columns. But what you can do with GBM models is build a GBM model, supervised learned GBM model, and take the split points as features going back into your GLM model, or create a deep learning model. And what you can do is take the hidden layers in a in a neural network as ways to generate basically features. The new hidden neurons in a hidden layer is essentially your new features in a way, almost doing a dimensionality reduction on your feature set, but except you can always join it back to the original feature set so that you have all the features that you could possibly want. There's improvements that you can do externally. You can add data, weather data, not just for Chicago, but for airlines outside of, from the origin point instead of just the destination points. And in general, the instrument that you use to do this process, be it R, Python, or Flow, there are sort of pros and cons to each. In Flow, everything's a little more graphical. You can point and click through everything. You can sort of explore without having to write too many lines of code. R and Python is great for people who know how to, who wants to filter the data set, who knows what they want to group by, functionalities that's not allowed in Flow. And these expressions are running parallel and distributed in the same way that the algorithms and the model builds are running parallel and distributed. And then what's great about running it in R and Python versus in Flow is that you're able to run loops. You can do a grid search in Flow as well, but in particular, if you want to run certain parameters and loops, your own grid, you can just use a grid function in R to create the grid of parameters and run it in a loop to build many models, sort it by the best performance metric, and then pick the model that works best for you. And then from the Flow UI as well, you can also readily access the POJO, which we mentioned earlier, which is the Java representation of the model that you built. All the models that we built today, or the models I built here via R Python, is available as a plain old Java object. So even though I was typing R code and Python code, what the software developer eventually takes into production is still the same line of code. In Python in particular, you can create an assembly of munging capabilities as well that you can save out and built into a pipeline so that new features or new data coming in will get munged before they are scored on the model that you built. And that is the end of my slides. If there's any questions, please ask. Otherwise, I don't really have any more scripts to show you, except if you're interested in sparkling water, I can also go into a little bit of that as well. But any questions? Oh, yes. Oh. Oh, technical assistant. Tom? Avni? Nick? Okay. Someone's coming to you, hopefully. Oh, sorry. Yes. I might have to throw you a microphone. Do you mind if you catch a microphone? I can't hear you. Ready? 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 Oh, sorry. Go ahead.
Is this a microphone?
Oh, there you are. It works.
You mentioned sparkling water. Can you show us some sparkling water, please?
Oh, sure. I mean, I could. Is there any other questions besides the sparkling water?
Any insights why GPM is outperforming GLM?
Oh, any reasons why? You can, but I think I heard. Any reason why GBM is outperforming GLM? Well, GBM is just a tree-based model, and instead of just splitting by, oh, right here. Thank you. It splits by, you can do splits like, it matters more if you're using a certain airline out of one particular airport versus that airline in general, right? So if you're flying from, let's say, you're using JetBlue flying out of New York, it's going to be great. This is the hub for JetBlue. If you are using JetBlue flying out of, let's say, I don't know, Seattle, it might not be as great. So little things like that, it's not, this feature directly has this value for the response variable. There's little interactions, details in there that you might not get from a GLM model. Yeah. Yes?
From a performance perspective, which one works better? Because Python or
No, I mean, for our Python and Flow, there's the thing is that everything goes through the same recipe API. You saw that the code were very similar for each of the different scripts. There is no really real performance difference. There might be certain different behaviors between Python and R in terms of how temporary frames are created and garbage collected out. So that there might be a difference there, but there's no performance issues in terms of how the algorithms and tasks are being run. Sorry, do you mind if we get that one first? Yes. We have our own library. So that's the H2O library that you installed. Everything that's in the H2O library are the supported functions for an H2O frame.
So if I use like this GPM in H2O, then I'm attack using H2O implementation of GPM.
Yes. 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 Exactly. And there's ways to translate, let's say, a GLM model built by GlimNet into an H2O model with the POJO representation. There's a way to create, let's say, a GLM object based on the coefficients. So you can translate that. And there's also TensorFlow, for example. You can translate a TensorFlow model into an H2O deep learning model by just exporting out the weights and biases from a neural network in TensorFlow into H2O and then create the H2O representation of that deep learning model. Yes?
Question about the model. So say you have built a model
Yes.
based on the 24 months data in the past, and in the next month the new data coming. So instead of retrain the model,
Yes.
build the model using the new, like 24 months frame.
You want to continue building a model without using the old data.
Yeah, to adjust the model to digest the new months data.
So you might not want to do that. The capability is there. It depends on of how your data set works. Maybe it doesn't matter so much. But there is a capability in GBM and deep learning where you can checkpoint the model and pass it a new frame, and it will continue learning from the old model. So you just have to specify the checkpoint, and it will continue to learn. Yeah. Yeah, I would rebuild. In general, I would just rebuild the model. I want to see if there's changes with the new data set included, rather than, to me, it doesn't make direct sense to just use the model and train on the new frame. It doesn't make intuitive sense quite yet. So maybe it makes sense for other data scientists, but
Yeah, but you don't have the model, you already have the
use models parameters initial.
Oh yeah, if you want to use the initial parameters, that's fine. If you can just save the parameters. That's you can sort of this is sort of like a model management process. If you pick the best parameters for your 24-month-old data, and you want to use that same parameter for your new model build, that's totally easy. You can just save out the parameters to a CSV file and read it back in and build with the same exact parameters. Yeah. Sorry, I think you had another question earlier.
I just wanted to ask if you have a Scala shell it works. So both R and Python.
Yeah, Scala also works. So Scala, the Scala implementation is with Spark in particular, and I can show a little bit of that, which someone also mentioned earlier over there. I can show a little bit of sparkling water. Oh, you're taking, OK. So this is a sparkling water installation. I don't think we have it on the USB drives, but you can get it online. It's essentially an integration into an already existing Spark installation. So this points to a pre-existing Spark home. So I have defined here, I'm going to just show you really quickly, echo Spark home. I already have a Spark 1.6 installation on my laptop. And it's set to my Spark home. This is my Spark installation. And you can view, when I do something like sparkling shell, you can see that it's essentially setting a bunch of environmental variables, exporting those out. And then at the end here, this is where you execute the Spark shell. It essentially goes to the Spark home, executes the Spark shell with the addition of the jar, H2O jar file. And so what this means is I can show you a script. VI examples. And we're just going to use the same airline script. There's a few other ones in there if you're interested. But essentially, you import the Spark context, you import H2O context, you spin up H2O inside of a Spark executor node so that it shares the same resource pool. So the amount of memory you allocate to a sparkling water cluster, both Spark and H2O has to share it. And if I go scroll all the way down here, here it's reading in the data set. So I'm reading it in using this one. I'm reading the data right into H2O. So you can do basically a get of the file and wrap the H2O frame around it. Here I'm reading the data, weather data, into Spark, whereby I just use Spark context and the text file command to read in the text. And here I can transform a airlines table that I read in as a Spark, as an H2O frame, as a Spark RDD. And then I can transform it to basically a Spark RDD that I can register as a table for a SQL context, for a SQL join of the flights and weather data. So you can write SQL queries on an H2O frame wrapped as a temporary table. Yes? Where's the file? It's in the installation of sparkling water. So if you install sparkling water from our website, it should be in a directory called examples and scripts. And the data is all contained in the installation as well, so you can test that out as well. So so right here is the code to run the deep learning model instead of GBM here. So it's very similar. You have to import the deep learning class, and then you set the parameters. And then down here, you do a new deep learning model with all those parameters. And similar to Python, you ask it to train on the data set. And then it just builds a model. And you can do things like predict is called score in Scala. And you can score inside H2O using Scala code. And again, on the bottom here, this is just the same GLM build. You can see alpha is set here, response variable. It's all the same. So again, it's making the same API calls as all the other client interfaces. Any other questions? I have 5 minutes left. Or we can just end early. Yes, go ahead. I can't hear you. Can you use the mic? I'm sorry. Thank you.
All right, so the diagram which you showed earlier about
The ROC curve?
the chunks,
Oh, the chunks, yes.
right? I'm more interested in the fault tolerance. How does it work? Let's say one of the node goes down.
Yes.
So you said there's a R pointer, header. And
Yes.
So I'm curious on that architecture. How, I mean, is it something a part of this?
So H2O nodes cluster up when you start it, and if a node dies, there's really no way of recovering from that. Everything sits in memory. A node dies, it basically spirals downward from there. All the other nodes side, there's no writing out to disk. So you just have to make sure there's enough memory so that you don't run out of memory or your cluster don't die. Typically, it's a long-running task where none of the H2O nodes should come down. Yeah. Yes?
Yeah, does H2O output a PMML score of the models?
The PML, oh, the PML, sorry, the PMML representation of, we don't currently export as a PMML. Again, a lot of the functionalities we built into H2O is customer-based. So it depends on what our customer has asked for and how they put things into production. For example, you know, the scoring using the Pojo is a nano-fast scoring engine. It's already ready to execute if you can read or Java, you can execute Java code. So there's really no need to export it as a PMML. It's sort of an extra step for a lot of people to export it as a PMML, and they have their own translator to translate the PMML into either C or Java code. Yes?
Yeah, actually, I have a follow-up question on this one. So as you said, you don't really output your model, translate your model output PMML, but what if, like, say, some clients have the model trained, like, say, in SAS, and then is in PMML format? Is H2O able to consume that?
So at the moment, no. We're building new things into the enterprise level product of H2O all the time. If a customer specifically requests it, and is in a contract, we'll do it. I mean, like, the Pojo wasn't, you know, didn't exist when H2O first came out. It was added. So it's doable. It just hasn't been done, and it requires development work. Yeah, developer work. OK? All right. Thank you, everyone.